called geostrophic balance. So geostrophic means earth turning, and then balance is obviously balance. This is a balance between the pressure gradient force and the Coriolis force. So here's what happens. So this is a little bit more complicated than the map that I showed you a few moments ago, but really the same idea is here. So we have high pressure down here to the south. Well, yeah, actually, let me put a nice little north sign right here, in for north. There we go. Got our north sign. And we have low pressure on the top of the map, on the north of the map. And then we have our particle. And our particle, let me actually pull up my laser pointer. Our particle is right here. Now, if the particle is at rest and it's released from at rest, there is no Coriolis force acting on it. And the reason why is because it's not moving. The Coriolis force is determined by the speed of the wind. The pressure gradient force, however, is not. It is determined solely by the difference in distance between this high and low pressure. If you remember from an earlier lab, when these isobar lines are very close together, that's a stronger wind. When they're further apart, that's a weaker wind. Well, here's what happens. Suppose I let go of this parcel of air. Well, because of the pressure gradient force and because there is this striving for equilibrium in the natural system, the particle of air will begin to accelerate towards lower pressure. Again, that's the pressure gradient force. And as it's accelerating, its speed is increasing. And as its speed is increasing, it is going to begin to feel a deflection to the right caused by the Coriolis force. So as the particle of air is accelerating, it's going to actually begin to turn to the right. Now, as it turns to the right, the direction of the pressure gradient force does not change. But because the Coriolis force is acting on the wind, that causes the particle of air to turn to the right. Well, eventually what's going to happen is, as the particle continues to speed up faster and faster and faster, the Coriolis force is going to get stronger and stronger and stronger. Now, what will eventually happen is, as the wind continues to turn to the right, it will eventually reach a situation where the pressure gradient force is tugging it in one direction, and the Coriolis force is tugging it in the exact opposite direction. And the two cancel each other out. That's the idea of geostrophic balance. The pressure gradient force and the Coriolis force have now canceled each other out. Now, Terrence, why is the wind still going, though? Why is this air particle still going? Well, I'm glad you asked. Remember, the law of inertia states that an object in motion stays in motion unless it's acted upon by a net force. Between points A and C, there was a net force acting on the particle, which caused it to continue to accelerate. However, once the particle reached point C, the forces were now blowing in the opposite direction. They were pulling the particle in the opposite direction, and therefore they canceled each other out. The net force is now 0, and the particle will just continue in its current motion unimpeded. It'll just continue in its current motion. The only thing that's going to change the speed of the particle is if the pressure gradient force weakens or strengthens, or if the particle is near the surface of the Earth. Now what happens is, here at point D, this actually demonstrates a particle near the surface of the Earth. And, excuse me, and the way that a particle near the surface of the Earth works is, you've got the pressure gradient force pulling the wind towards low pressure. You've got the Coriolis force pulling the wind to its right, but you also have friction pulling back on the wind. And what this actually does, is this causes the wind to slow down. And the slowing down of the wind weakens the Coriolis force, making the pressure gradient force the strongest of the three. That causes the wind to then begin to turn back towards that low pressure. And it actually turns back at an angle of 30 degrees relative to the nearest isobars. Okay, now with that said, let's actually break the wind up into these three components. So let's actually take a station model, and let's actually break the wind up into these three individual components. And this is the last thing that you'll need to do for this lab. So here's how it works. So the black line I'm going to draw represents the net wind. The red line will represent the pressure gradient force, the blue line the Coriolis force, and the brown line friction. All right, so let's do it. First off, you're going to be asked on this model or on this assignment to draw the direction the wind is headed towards. Now remember though, these station models only tell you about where the wind has come from. They don't tell you where it's going. They only tell you where it's come from. Now here's the good news. The good news is where it's going is just the opposite direction. So in this case, the wind was coming from the west-southwest, and therefore, since it was coming from the west-southwest, it is blowing in the net direction to the east-northeast, like so. And so I'm drawing my black arrow, indicating that the wind is going to the east-northeast. And forgive the terrible chicken scratch there. But yeah, it's going to the east-northeast. Now let's actually split the wind up into its individual components. The first one we need to look at is the pressure gradient force, which is in red. And the way that the pressure gradient force works is you identify the nearest isobar to the station. So we have the station here. The nearest isobar is right here. And what you're going to do is you're going to draw a red line that is exactly perpendicular to the isobar, pointing at low pressure. So it's going to look something like that. It's going to look something like that. And I think that actually looks pretty good. The next one that you're going to draw, and so that indicates what direction the pressure gradient force is pulling the wind towards. The next force you're going to draw is the Coriolis force. And that I will do in blue to honor this color here. And the Coriolis force will be 90 degrees to the right of the wind's path. So since the wind was blowing this way, and I actually messed up my arrow a little bit, the Coriolis force is going to be 90 degrees to the right of that path. So there's my Coriolis force wind. Okay, there's my Coriolis force wind. And actually that looks terrible because it's overlapping, so maybe I'll just draw it like that. But there's my Coriolis force wind. And then finally, the last wind that they want you to draw is friction. And friction's pretty simple. It's literally just in the opposite direction that the wind is blowing towards. So if you want a nice little trick, see where the wind barb is pointing? That's where friction would be pointing. So let me pull up my highlighter again. And so friction would be going that way. And that splits the wind up into the individual components. So again, pressure gradient, that's going to be perpendicular to the nearest isobar and pointing towards low pressure. Coriolis to the right of the net direction, not the pressure gradient direction, to the right of the net direction that the wind is traveling in. And then friction directly behind where the wind is blowing. And that's really all that you need to know for this lab. As always, if you have questions, comments, concerns, please feel free to email me, and I will include the link to that demonstration video. And that's it. Best luck on this lab. It is one of the tougher labs of the course, but you've got this, all right? Just let me know if you need any help. Let me take a moment.